Thank you. So how many people have been here since Wednesday? Great, me too. So I have been participating in the President's Forum and then in a lot of the sessions yesterday, and I am just brimming with new ideas and trying to synthesize and integrate all of the stuff I'm hearing. So I last night changed what I was going to talk about today to try and touch on what I was hearing, especially in the sessions around ePortfolio. Because one of the things I was hearing is, and you can tell me if I've just misheard, but that it's advancing to the point where some of the focus now is not just on how do we design ePortfolio practices for our learners, but how do we collect evidence? How do we do research and collect evidence for two reasons? One of them to inform how we design the activities we give our students with ePortfolios, but secondly, to begin to collect evidence of effectiveness so that we can start to get a wider community of practice around using this approach. So I thought I would talk about developing liberal learners in a digital age, but then the subtext is what's new. The science of learning, technology, and liberal education. How do those three strands come together at this point in time? So I thought I should start off talking a little bit about the science of learning, because probably that's the one that is least familiar to the group we have. How many people in this room consider themselves learning scientists as your primary? Okay, so we got a couple of you here. So I would say simplistically, the goal of the science of learning is simply to describe, explain, and predict human learning, as is the goal of almost any science. What's particularly interesting to me about the science of learning is where it's situated. And by that I mean I'm pulling on an argument made by Stokes quite a while ago, looking at the tension, what was then reported as the tension between basic science and applied science. So where do we situate our research? And this was, Stokes created this idea of Pasteur's quadrant. Now, if you look on the y-axis, the emphasis is a low emphasis on basic science or a high emphasis on basic science. That means to what degree are we conducting our research to make progress on our fundamental understanding? And in this case, it would be our fundamental understanding of human learning, how learning happens. And if you have a high emphasis on basic science and a low emphasis on application, that was called Bohr's quadrant, after Niels Bohr. You can see that this quadrant was not really developed for learning researchers. It was more for sort of physics, really. So if you have a high emphasis on basic science and a low emphasis on applied work, you're situated in Bohr's quadrant. The challenge of doing work in Bohr's quadrant is you can find results, but it's often difficult to think about how you translate that into real-world application. And we see this a lot in learning research, where we'll do tightly controlled lab studies and we'll come up with a finding such as massed versus spaced practice, or ways that we cognitively improve our memory. And then we publish these things in journals, in our journals, and they're journals that often chemistry faculty, English faculty, history faculty do not read. And they're pretty jargon-laden. So even if those faculty were to attempt to read those journals and understand this finding that we came up with, there's a real problem about how do I translate that into my own teaching practice. So that's the challenge with Bohr's quadrant. The other place that learning researchers work is in what's called Edison's quadrant, where we have a low emphasis on the basic science. We're not trying to understand the fundamental mechanisms of human learning, but we're trying to solve a real-world problem. And I would say that most of the research that I've heard at the conference so far, I would say, is pretty squarely in Edison's quadrant, where people are are experimenting, doing practice, you get great little pilot studies, little examples of how you can do a very robust practice and solve a real-world problem. And that real-world problem might be keeping more students engaged in the chemistry sequence, in the sophomore chemistry sequence, or something like that. You have a real-world problem. People don't get equilibrium. Can we design something that will help them with that process? And the challenge there is, while we can make it work really well in that particular situation, how do we get it to travel? We can't abstract principles that can then be applied in new contexts and new questions. So that's Edison's quadrant. Then there's also actually low emphasis on basic science, low emphasis on applied work. People really do research in that area. Some people call that Peterson's quadrant after, the Peterson bird stuff. I just tell my students, that's the quadrant that NSF will not fund. Stay out of that quadrant. My argument is that where education and learning research should occur is in Pasteur's quadrant, where we can construct our learning interventions in a way that both help us make progress on our fundamental understanding of human learning, while at the same time we are solving real-world educational challenges. But in order to operate in Pasteur's quadrant, I would argue, is not a solo activity. We need to co-construct the learning interventions. So get the people who are learning about learning, who have things they want to understand about the basic science of learning, with the disciplinary faculty, with the software engineers, with the human-computer interaction, with the whole collection of people, and co-construct the learning intervention so that we can make progress on both our fundamental understanding of human learning and solving whatever the real-world educational challenge is. Okay, so with that, I'm now going to ask the question that I love to ask big rooms full of people when we're talking about digital learning. Some of you may have heard me ask you this question because I did ask this question on the very first day. So what are the affordances of the technology? Why is everyone so excited about digital technology transforming, improving higher education? And when I ask in a room, I get 3 answers. The first one, and this used to be the most common answer, is access and convenience. If you have a computer connected to the internet, you can learn anytime, any place. Access, convenience. It's what's going to change higher education. The second answer, and probably the one that, if you're familiar with my work, I've been pushing for the last 12 years, is really the middle one: simulation and personalization. We can actually do things with the technology that it's really hard to do in a regular classroom. In an engineering course, we can have students construct a bridge, and nobody gets killed. In biology, we can see things at a microscopic level that we can't see in a real-world classroom. In a literature course, we can have students closely read a text and collectively annotate and see each other's annotations and engage in a discourse around a text that's really hard to do in a larger and in-person classroom. So simulation, then personalization. That seems to be the big catchword now, where we can use the technology to essentially personalize the learning experience to each individual learner where they are. So that's simulation, personalization. The third one, which is the one that I think my guess is most people here are going to vote for, I'll just, stack the deck, connection and synthesis. That these computers are connected to an internet. And that means that we can connect our learners to resources, to each other, to experts, to the world. so they can get connected to all these different assets, and we can ask them, as we do in e-portfolios, to synthesize all those different discrete parts and create something new. So connection and synthesis. Okay, so now I'm going to make you vote. So how many people, by show of hands, think that the big power of this technology, what's going to transform education, is access and convenience? Don't be shy if you think that's what it is. Go ahead, raise your hand. Okay, great. How many people think it's simulation and personalization? That's the real power. Got to get a few more there. Okay. How many people think it's connection and synthesis? Yeah, it's what I expected from this group. But you see, there's still a little bit. Okay, so now how many people, and I like to ask this too, how many people think, Candace, that is a bad multiple choice question? And wanted me to have all of the above. Anybody for none of the above? Okay, so I agree with you. Okay, but it's good to just to force you to choose, just so you can see where you're coming from. But I agree that all of these things are the power. But I also think none of these things are the biggest power. I would argue that the biggest power is that it's kind of what I like to say Google has figured out. It's what Amazon has figured out. It's what Netflix has figured out. What is that? That you don't use the technology to push stuff out, but just to push it as far out as the interface. Because in that interface, we can observe. We can observe the user. Now, whether you like it or not, Netflix, Amazon, Google, Facebook, you name it, are observing our interactions in their interface all the time. And they're doing it for a very particular reason. One reason is personalization. They're trying to know you as an individual consumer better so they can target things that they think will meet your needs better. But they're also observing us collectively as consumers so they can understand us better globally as consumers. Now, that sort of saying, okay, we're going to do that, seems, how many people think that's really uncomfortable that you're even talking like that, Candace? Okay, because what we're looking at is the intention to view us as consumers is where we are different. Because we're looking at the users not as consumers, but as learners. And I make a very clear distinction between learners and consumers in spite of the productivity narrative that seems to be out there. Learners are not consumers, they're learners. But we can, by observing their interactions in well-designed interfaces, get to know them better as learners, both so that we can help personalize the learning experience, but for what gets me excited is we can learn about learning. The power of these technologies is it can make the learning process visible. And once it's visible, it is amenable to scientific study. So what we have is the students interacting with these environments, and then what we're doing in the environments is collecting that interaction as data. That's the other thing I've heard a lot is people throwing around the word data, data, data. And I think in the next phase, we need to get much more specific about what we mean by data. Because just collecting the click stream, which is what a lot of people mean when they say, big data in education, just collecting the click stream doesn't give us the information that we need to be able to truly understand, make visible human learning. We need to design the environments so that they're collecting data that is meaningful to us to be able to understand what's happening. Because if I just know at 7:37 a.m., student X clicked pixel 237, that doesn't really tell me anything. That doesn't make that learner's thought process visible. Okay, so we can use this data to drive these very powerful feedback loops. One of them is to the learner. And so we want to construct environments so as learners are practicing outside of class, we can give them context-specific and targeted feedback to support their learning process. But that requires us to really think through what is it we want the learner to be able to learn, and how do we design an environment that will allow us to provide that kind of support to the learner. The other feedback loop is to the instructor, and then to the course design team, and to the science of learning. And I'm going to take each of those individually. So first one, to the learner. So when the work that I was doing, that I started at Carnegie Mellon and am now continuing on at Stanford, was this project called the Open Learning Initiative. And what we did in my Carnegie Mellon days was, and we talk about this project as bringing together learning science with technology to design effective environments. At Carnegie Mellon, the dominant thread of learning science is cognitive science. So we spent a lot of time essentially taking these complex skills and concepts and tasks that we want students to be able to do and deconstructing them, doing cognitive task analysis, and designing environments that would support students to build those cognitive competencies. Very successful. We had this isn't the purpose of this talk, but happy to share we had really demonstrable results in being able to support learners to develop these cognitive skills. I'm not going to show you examples, but the other thing is it wasn't all learners. And one of the things that I've also heard as a real theme this week is the diversity of the learner. And I don't just mean racial, cultural, socioeconomic, gender diversity. Those diversities are critically important to consider when we are designing environments, but they're not the only diversities. We also need to look at the diversity of our learners when they come into our learning experience, the diversity of their background knowledge, their relevant skills, and their future goals. I'm often asked, why do I think technology is going to help us here in education? Why can't we just keep doing what we've always done? And it's because the context has changed. Back when we had a fewer number of students, but not just a fewer number of students, a more homogeneous student body, then our processes and approaches worked really well. What we're being asked as faculty and institutions to do now, which is not only serve a greater number of students, but serve a greater diversity of students along these dimensions, is not doable without better tools and support. So I'm not trying to replace faculty with computers. I'm trying to create technologies that will be better tools to support faculty and learners in the learning experience. Because now, in the cognitive side, we attended very much to this diversity. But but there's more. Wait, there's more. There's even more diversity, because there's more diversity in learner attributions. How learners interpret and explain the learning experiences they're happening. And for this level of diversity, I'm fortunate enough to be at Stanford, where I have many research colleagues who are looking at this side of the learning experience. For example, how many of you are familiar with my colleague Carol Dweck? Okay, so I don't have to go. So Carol Dweck does work in mindset, and we found a lot of evidence that the student's mindset, whether they believe that their intelligence or their skills are fixed or whether they're malleable, is very informative to how well they will be successful in learning. So in the next round of OLI courses, we are intentionally building theory-based interventions that attend to supporting students to develop a growth as opposed to a fixed mindset. But even outside of the student's mind, there are social, environmental, and social psychological factors to which we need to attend. And fortunately, I have colleagues at Stanford that are also exploring and working with me in these areas. Two I will speak to is social belongingness, Jeff Cohen's work, around the degree to which, especially for first-generation students, the degree to which they feel like they belong in the learning environment and the impact that has on their ability to learn, and interventions that we can do to support the learner's sense of social belongingness. And then also from my former dean, Claude Steele, who did a lot of work in Stereotype Threat. People familiar with Claude's work? Yeah, and this is, sometimes people confuse stereotype threat with internalized oppression or internalized stereotype, and it's different than that. Students that are experiencing or having their performance degraded by stereotype threat do not believe the stereotype about themselves. It's not that I'm a woman mathematician and I believe that women aren't as good at math, or that I'm an African-American student and I believe that African-American students aren't as academically competent. I do not believe that stereotype. The threat comes when I believe that others in my environment believe that stereotype and see me as a learner through that stereotype. And Claude has shown in multiple studies that just the belief, just that threat being in the air, statistically significantly degrades the performance of the learner. And you can take that same learner and put them in a context where stereotype threat is not, and their performance is completely changed. So I think it's really important to be looking at how we're designing our environments in a way that either mitigates or exacerbates the potential of the learner experiencing a threat to their identity. Okay, so that's about the learner. Now the instructor. So I am a faculty member, and I do, some people say, eat my own dog food. I like to say, drink my own champagne. And so I use the OLI courses that were co-developed by multiple people. I used it last quarter, actually, to support teaching a data analysis class I was teaching at Stanford. And what I would do, I did not use the technology in the classroom. It was not a whiteboard thing like that. What I do is, instead of having the students use a traditional textbook, I tell them to work through a module of the OLI environment. So I taught on Tuesdays and Thursdays. So I would tell them on Thursday, work through module 3 of the OLI course by 10 o'clock Monday night. Finish working through it by 10 o'clock Monday night. Because between 10 o'clock Monday night and 10 o'clock Tuesday morning, I'm going to look at the results, the analysis of the data that's generated by their interactions. Now, the results that I'm looking at are not, I gave them 10 questions on compute the median, I'm going to see if they got 8 out of 10 right. That's not the kind of data. Instead, all the complex tasks, interactions in which they're engaged, they don't know that what I'm testing is, can they compute the median? They're just trying to solve a real-world data analysis problem. But the moves that they're making are semantically tagged so that the computer knows when they struggle right there, that probably means that they're struggling with computing the median. And the computer can collect over all these more authentic tasks those discrete skills and run them through an underlying cognitive model that we built ahead of time, and to make a prediction to me as the instructor, how well is an individual student or my class as a whole doing on these larger learning goals that I value. So what I get to see is not how many they got right or wrong, but the instructor learning dashboard. Now, what's different about this dashboard than a lot of other predictive analytic dashboards, there are some things that are the same, like the green orange, red. That pretty much shows everywhere. So we know that green means students in that area are doing great. We would predict that if I gave them an assessment on that outcome, they would nail it. Students in orange, moderate. Students in red, that means those students are trying, they are not getting it. If I were to give them an assessment today on relating the measures of center and spread to the shape of a distribution and choose the appropriate measures in different contexts, that's the larger goal. I want them, if I give them, these data, can they create these graphical representations and interpret them? That the students in red, if I gave them an assessment today, they would not do well on it. How about gray? Anybody have a guess what gray means? Yeah, it means they haven't done enough work in the system since last Thursday that running it through the cognitive model, we can make any kind of reliable prediction about the student's knowledge state. So I can, as you can see, if I actually don't look at this until 9:30 on Tuesday morning, I could quickly see of the larger outcomes that I was hoping the students would achieve, where should I focus my attention? And you can see that these are the goals that I would really want them to learn from having worked through that module in much greater grain size. I can also click in to any of those bars if I've got a little more time and see which students are in that are at that level of achievement. And I remove their names because, well, you guys understand why. And it also tells me how many activities they attempted in that module that's feeding that prediction. Now, I could click on any of those students' names and see the learning profile for that individual student as well. Also, on the other side, that larger outcome, relate the centers of measure and spread to the shape of a distribution and choose the appropriate measure in context, that has some sub-skills that are associated with it. So I can look at, well, is the struggling that they're having because there's a sub-skill. So I can drill down a little bit more to see where do I need to focus. So you can see that compute the median is an area that the students are struggling with. I could actually click in further on compute the median and look at all of the tasks that are feeding that prediction about compute the median to try and get insight into where they're struggling with compute the median. So using the technology to collect and analyze the data to give the instructor much more robust information to help support the in-class teaching. Okay, then there's the course design team. Now these environments that we create are used by individual learners, and they get feedback based on their data. They're used by individual faculty to teach courses, and the individual faculty get the feedback based on their class's data. But the environments are used not in an individual class, but are used in, like last quarter, the statistics course that I was using to teach my course at Stanford was also being used at Santa Ana Community College, at Berkeley, at Bryn Mawr. I mean, a diversity of institutions using the same environment to support their teaching and learning. They weren't all using it exactly the same way. It's a resource, it's a tool, it's not a pre-packaged standardized course. So the team that designed this environment gets the data from all of those courses. And when I say the team, I mean a team. So we bring together learning researchers, software engineers, human-computer interaction experts, universal design for learning experts, the faculty in the discipline, and students to co-create these environments. And then when we get the data back from all of the environments that ran that quarter, we can target where in our design do we need to refine it. Where are students not getting it? Where do we need to refine the cognitive model? Where do we need to refine the learning activities? And the last group, near and dear to my heart, are the learning researchers. So I started off talking about methods in learning science. And the two methods that I think I talked about were, and this is what we've historically done, are these randomized controlled trials, usually in a lab, where we can tightly control the variables and make really good, internally valid predictions about what shifts learning. The problem with that and that's what we often publish in our journals. The problem is, as I already mentioned, how do you translate that to the real world? And when you take something that we did in a randomized controlled trial, in a lab study, and you put it out into the real world, it often breaks down. So this gold standard of randomized controlled trials often doesn't work really well when it comes to educational research. So the other kind of research, which I know a lot of people here do, are classroom studies. Come up with a pilot project, do an intervention, follow the classroom over a long period of time. These are much better for ecological validity because we see students learning in real learning contexts. The challenge there is often that there are so many things that you're doing and so many things going on, it's really hard to make a replicable causal claim. And you'll see this, where someone will say, look at this great thing I did, and someone else will say, oh, that's cool, I want to do that in my class, and I'll try and do it in my class, and I don't get the same effect. And I would argue that that's because we don't really understand what the causal mechanisms or the interaction of the causal mechanisms were that really caused the effect. And I liken this to when I'm teaching expert novice stuff, that oftentimes what novices do when they're trying to learn something is they map on surface features. The famous studies where they took physics problems and had physicists group them, and they grouped them by the underlying problem that you would need to solve to be able to do the problem. And they gave that same stack of problems to physics students to group, and they grouped them by surface features. Oh, this has an inclined plane. This has a pulley. And that's a real difference between expertise and novices. And I would argue that we are all still novices in this space. So when we try and replicate somebody else's successful intervention, very often we're going to map on the surface features, and we don't really know what the deep features are that are causing the change. So that's so we've got these two challenges with our traditional methodology, and this is where web-based learning environments solve our problem. This is the power of the technology, is we can essentially get the best of both worlds. We can, having the researchers and the practitioners work together, design the environments so that they help us make progress on our fundamental understanding of human learning, so we understand what's actually causing the change at the same time that we're solving real-world problems. And that puts us, happily, squarely in past year's quadrant. So I only have a couple more minutes, but so the kinds of data that we collect off of these learning environments historically, these are the kinds of representations that the learning researchers see. So Marlene Scardamelia up at the University of Toronto, her unit of study is not an individual learner, as that was my unit of study, was the individual learner. Her unit of study is really the group. And can we construct knowledge-building communities? So we collect the same data, but the way she's analyzing the data is essentially doing kind of a network analysis. So those nodes are individuals. The lines are the connections, are the discourse connections between the individuals. So at the beginning of a learning experience, you have pretty much the teacher in the center and everybody connecting to the teacher, or some pods of expertise. And what she's trying to do is move towards a web of a knowledge-building community where the students are all making moves in the environment where they're co-creating and taking responsibility for expertise. So that's the kind of transition she's looking for in the data and facilitating to occur. The data, this is a data representation from the Pittsburgh Science of Learning data shop. This would be on a knowledge component, like compute the median, where we would see the y-axis is the number of hints and the amount of feedback that the student needed at the time they were on some subtask in a larger complex task where we had tagged that action as compute the median. So the y-axis is a function of the amount of support or tries they needed before they could effectively execute that knowledge component. The x-axis is the number of opportunities they had to demonstrate that. So that would be lots of activities where over the course of doing data analysis, they have to compute the median in multiple tasks over the semester. So this is a kind of learning curve we like to see. This means that learning is happening, because when they were first confronted with having to compute the median in a more complex task, they were hitting that hint button saying, what am I supposed to do here? Or they made a move and they got feedback on it to refine their performance. So that's high support. And over time, it's sloping down. So then when they were more fluidly, as they were coming across a task where they had to compute the median, they didn't really need they didn't have to ask for a hint. They didn't make a move that reflected that they didn't get what was going on. So these are the kind of these are not the way the learning curves always look, but these learning curves can show us inflection points or flattenings where we need to redesign the environment or redesign our cognitive model. So now I'm going to just show a little demonstration of the new data analysis tools allow us to do different kinds of data representations. And this was done by one of my doctoral students who is in computer science. And he scraped essentially multiple states off of an open website called the Hour of Code, where over 1 million people have attempted to solve this particular computer science coding problem. And what he is working on in collaboration with some of my education doctoral students is, can we use the data that we can scrape off of these open environments to more automatically generate support? So this was his representation of the data of students trying to solve this programming problem. So the pink blob is all of the students, the millions of students that are trying to solve this programming problem. The nodes are different states. So if they write this line of code, that's one state. They write another line of code, it's another state. The edges are when we talk to teachers, computer science teachers, what would they expect a student to do from one state to the next state? So if you were just having a teacher design the environment, those edges are where they would give feedback or coaching or support. Okay, so let me show you. So as the students, so you can see a lot of students do the first thing. You can see now this big pink blob is going to break up because individual students do different things. And a couple things to notice, which is they're going all over the place. This is a very simple programming problem. And you would expect a pretty linear process, but that is not at all what the data shows us. And the other thing to notice is that the students aren't really following the lines that a teacher would expect the students to do. So our ability to predict what a student is going to do is actually quite poor. I should say that green, when the dots turn green, that's the solution state. They solved the programming problem. So it's kind of cool because you can look at these different data representations and you can also create art out of them. I'll stop that. And this gets me to my big ta-da, which is that in order to design these environments effectively, in order to transform education, we actually need to come from both directions. We need to start with what we think we know about human learning, so theory-driven, and in these environments we can construct testable hypotheses to refine our understanding of human learning. And we also can take advantage of these great tools that we now have as a result of big data. We can do data mining, as my students do, natural language processing, the statistical modeling and machine learning to help inform to help identify and inform what are the patterns we're seeing that we wouldn't have even imagined from our testable hypotheses. And bringing these two together, these two approaches together, is what is going to help us build better explanatory and predictive models of human learning to inform the design of our environments. And this sets up what I like to call the virtuous cycle of continuous improvement, which is we can start with what we know about human learning to design our learning experiences, and then we can use the technology part of those learning experiences to do what it does really well, which is collect data. And we can analyze that data to both refine our models and our theories of human learning and refine our learning experiences. And we set up this virtuous cycle within higher education. And I'm going to just leave you with two quotes. One is from a former colleague, the late Herb Simon at Carnegie Mellon. And Herb said, look at the date on this, 1991. Herb Simon said, improvement in post-secondary education will require converting teaching from a solo sport to a community-based research activity. And that is what I am inviting you to participate in, a community-based research activity. So that's the inspirational quote. The scary quote is from another economist from back 1967, William Baumol, who posited this theory of cost disease, which I won't explain, but it's really fascinating. But he said, without a complete revolution in our approach to teaching, we cannot go beyond current levels of productivity. Now, when I would use this quote last year or 2 years ago, my message was, such a revolution is possible. I've changed that because the truth is, such a revolution is happening. My question is the same. Who will lead it? And I implore us inside higher education, especially those who care deeply about liberal learning, to step out and lead this revolution. Because like it or not, these technologies are going to become a core part of our teaching and learning process for many, many students. And I think it is incumbent on us to define how these technologies are developed and used to support what kind of learning experience. So that's my challenge to you. And I think we have a few minutes for questions.
No.
No, we don't? Okay. Well, yeah, we have 6 minutes. One question?
No.
Pardon?
Sessions start at 9.
Oh, okay. Sorry.
Candace is
Okay.
here this morning, and then she's got to go to a board
Also,
meeting this
so
afternoon.
questions and questions or challenges. That's my email.
Yeah. Good. Thank you, Candace. One more time, please.